All right, let's get semantic. I'm Ray Myers. Welcome to Craft versus Cruft, and today I'd like to share a presentation that I'm preparing for a programming language semantics reading group that I'm part of. So, this is on attribute grammars. What are those? Attribute grammars are a modular approach to specify language semantics based on a context-free grammar. And we're going to assume for the purposes of this that you're already familiar with what most of those words mean. But the special thing here is that it's a modular approach. What is it that makes an approach to language semantics modular, and why did this one, Knuth argued, fit the bill? That is part of what is significant about this research. The main paper here that started it is Semantics of Context-Free Languages, which is by Knuth, 1968. Now, the mathematically inclined of you will realize that that is a long time ago. We are some 58 years later. And so, is this some historical relic? I think no. I think this is actually still relevant today. But in the area that got me into language semantics, which is formal methods and formal verification, not so much. You don't see it much over there. You see it a lot in compiler technology kind of community. So why is that? Why did this kind of foundational work in language semantics not end up near what I think of when I think of language semantics? That's something I wanted to try and understand as I approached understanding and presenting this paper. But first, let's talk about how attribute grammars themselves work. They add metadata, which is called the attributes in the attribute grammar, to the parse tree. So if you already understand how context-free languages are typically parsed, like with rules that are defined in B and F notation, for example, then you can picture adding data to the nodes on that tree. That's nothing revolutionary, and it wasn't new even then in 1968. But there was something very new about how these attributes behaved in the way that the data flow was implemented. It was both top-down and bottom-up. That was the key innovation here. So the data flow was bidirectional. The derivation rules that were there to assign these values, they could reference the child of the rule that you were on, or they could reference the parent. And so the terminology that's used here is that if you're referencing a children of the current node, then it is synthesized attribute. And if you reference your parents, then it's an inherited. So if it's top down, that's inherited attributes. If it's calculated bottom up, then it is a synthesized attribute. That's just the convention for this area. So Knuth's first example here is grammar for binary numbers. And not just any binary numbers, but they have a fractional component. And we're using the center dot there to represent what would be a decimal point in a decimal number, but of course it's a binary point technically, right? Because it's a binary number. But regardless, it's the fractional component to the right of that point. So a number might just have a string of ones and zeros, or it might have a string of ones and zeros and a binary point, and then another string of ones and zeros. That's what this grammar says in approximately BNF notation here. Now, we'll add semantics, and I would like you to pay attention here to whether we're dealing with synthesized or inherited attributes in each of these semantic rules. So this is, going to be your first taste of what a definition of attribute grammar rules actually look like. At the left, we have the grammar, and for each of these rules, we have how the values, the attributes we're going to assign to these nodes on the parse tree, how those are going to be calculated. So in this example, the semantics will serve the role of just converting the number, the string of digits, into its final numeric value. So at the bottom, you see the number, was going to be the final calculation. Let's step through these rules just briefly. You don't have to understand them fully. But at the bottom, it says if the value of 0 is going to be 0. That's the v. We're going to assign an attribute to be called v of 0 or 1 if it is 0 or 1. Simple enough. So then we have the L rule, right, which might be a binary digit, or it might be another L followed by a binary digit. So we can assemble arbitrarily many of them. And that is calculating v of L at the top based on v of b, and L of L, which is L for length, of 1 on the top rule, and the bottom one in the middle here is going to calculate it a little differently, but it's calculating the value of L1 based on the value of L2 and based on the value of B, and the length of L1 based on the length of L2 and adding 1 to that. So are these inherited attributes or synthesized attributes? Hopefully you're reaching the conclusion that they're synthesized attributes because they're all coming from the children, the ones on the right. So then finally the number at the top, the value of n is calculated based on the value of L. Is that inherited or synthesized? The value of n on the bottom here is calculated based on the value of L1, the value of L2, and then the length of L2. So again, that's all from the children. So these are all synthesized attributes. Everything in that example was a synthesized attribute. And that's unintuitive, says Knuth. It doesn't represent how we think about the problem. There's rules that are very complicated, and they reference things that are kind of all over the place. In this small example, it's somewhat tractable, but this is meant to represent a problem that just sort of compounds as language semantics get more and more complicated. So having the data flow in just one direction results in unintuitive semantics. So he wanted to be able, for instance, in the binary semantics example, to model it closer to how we think of it, right? Like this 1, 1, 0, 1, the value at each stage just being what that digit says, that's not really true. The value of this column is 8. That's the 8s column. This is the 4s column. This is the 0.25s column. That is a more intuitive way to think about what the values of different components of this binary string are. So what if we could depend in both directions? How might we define the semantics then? So we're going to add some components. So let me just define what all the attributes that are going to be at play are. There are in B, we'll have a value, which is a rational number. It is a scale, which is an integer. L will have a value, which is a rational number again, a length, which is an integer, and a scale, again, an integer. And the final number at the top just has that value, which is a rational number that we're computing. So these are the semantics here. And again, you don't need to understand, you can look at it later if you like, what the exact calculation and how that does arrive at the result. But let's think about which of these are being inherited, right? So here we're calculating the value of B based on S of B, or just hard coding 0. Here we're calculating the value of L based on the value of B, and the size of B based on the size of L. So that's going in the other direction, and so on and so forth, right? Like, and if you were to highlight exactly which ones are inherited, I think you'd get this. So let's look at what computing that would look like on an actual tree. So this is the parse tree of the string 1101.01, right? So this is, again, what you would get if you define that BNF grammar and then parse this string. But now we're going to run our semantics, but we can't run them all at once. They depend in all sorts of different directions. So let's run the ones we can. we can know that v of 0 is always 0, and we'll assign that, and we will synthesize, there's v, and we will synthesize the length bottom up. So this L is length of 1. This one can calculate based on that, length of 2, and so forth. We have length 1, length 2, length 3, length 4. All right? In our second pass, we will inherit the scale from the top down. So the scale of left of the dot will start at 0 and then increment as we go down from L to L. So size of 0, size of 1, size of 2, size of 3, and then the B's just inherited directly. They don't add 1. All right? So then we synthesize the value from the bottom up based on the size that we've just created, right? And so the value is calculated at B, and it is ultimately the final value. This is a value of 8. And so then we just take a sum up the tree. So this way of calculating this, it's more intuitive. The rules, there are a few more rules, and there is one more attribute than the other way is, but it just makes more sense. And he was right, I think, and we'll show some evidence that he was right later. This is said in the paper. The ability to let the whole tree influence the attributes of each node of the tree often leads to rules of semantics which are much simpler and which correspond to the way in which we actually understand the meanings involved. So basically, I mean, you do have more kind of dependencies going in different directions, but because you're able to get the information more to where it's needed, you have calculations that just make local sense. And that's what we mean when we say it's modular. But wait. Aren't bidirectional dependencies a bad idea? I mean, we could have cycles. This could cause all sorts of problems. You know, there's a reason this wasn't done before. And if you get a chance, watch this video where Knuth tells the story. But he recounts coming up with this, and it was actually his friend Peter that did. And he was saying, I don't know if I should make the semantics top down or bottom up. And Peter said, well, just do both. And he said, that's ridiculous. It would be circular, and is arguing about it for 10 minutes before he realizes, actually, there's no reason he couldn't do it. Because there's a solution to this problem, which is no. Cycles would be a problem, so no cycles are allowed. That's it. That's all we need to do. More formally, the semantic rules are well defined if and only if no directed graph contains an oriented cycle. And the graph we're talking about is the graph of the rules' dependencies on each other. So that's not actually that much of a problem, because we have algorithms for detecting if a graph has a cycle in it. So we can know up front if we're dealing with a grammar that is always going to give us valid results. So there's another example in this paper that I'm just going to show you. I'm not going to really go over it here, which is a toy language called Turing. And that's neat. We've got the tape and the Turing machine with various instructions here, and they define using attribute grammars, the semantics for that. It's in about a page. I think that the historical context for us now is a little more interesting, and then I'm going to show some more modern use of this. So very helpfully, although it's just in the context of a literature review there, but for me to help understand what world of semantics that already existed this was coming into, it listed what have been the contributions to formal semantics as Knuth understood them at the time, at that point in 1968. So we have de Backer's definitions of ALGOL 60 by means of growing Markovian algorithm. I don't know what a growing Markovian algorithm exists. Honestly, maybe you can check into that. This one was more influential, I think. Landon's definition of ALGOL 60 by means of lambda calculus, that led to what we now know as denotational semantics, but those terms were not yet being used. And John McCarthy, inventor of Lisp, actually also had his own little ALGOL run, a language he called microALGOL. And I'm not really sure what we would call his approach now, if we would even have a name for it. Then we have Nicholas Wirth and Weber define a language called Euler, which is also ALGOL. It's an extension of a generalization of some kind, as well as this one of PL1. So I'm trying to make sense of the historical world this is in and how it relates to what we know of other forms of semantics now. These are my observations, and I'm very new to this field. Please, if you know more about it, tell me what you observe and if I've got this right. This is just me trying to make sense of it. So it sticks out that in the literature now, operational semantics is huge, but it was not around to be referred to at the time. Actually, it was being developed at almost the same time, because with the ALGOL 68 report, that was what is credited as the invention of operational semantics. So that was being done around the same time. And they were doing ALGOL. They were doing lots of semantic work on ALGOL. It wasn't just, some toy research language like Turingall or whatever, but the one of the biggest industrial languages at the time was very harmonious with the programming language, computer science semantics work. And that's not really true anymore. They're not so closely linked. You're kind of going against the grain if you're trying to do formal semantics of a major industrial language now. But we also mean a different thing when we say formal now. Usually we're talking about mechanized semantics. You can put in a prover and do stuff with, and that wasn't something they were doing with their semantics just yet. It was on paper. And something else that sticks out to me is that the semantics is very much intermingled with parsing. Now it is more common to do semantics based on an abstract syntax tree that you've already figured out how you're going to parse. But at this time, they had not yet cleanly separated, I guess, the problem of parsing and the problem of assigning semantic behavior for whatever reason. If you think that's true or not, let me know. And what I suspect here, by the almost total absence of attribute grammars in the formal verification literature as I know it, that attribute grammars more enable better compiler engineering, but they don't appear to be that helpful for doing mechanized proofs. Is that true? I'd love to talk about that. However, they are referenced in lots of other places. There have been entire conferences held just on attribute grammars. They've had continuing influence. So here's one modern example. There's this really interesting system called Silver, which is a meta compiler, a language specifically for making things like compilers. From their page, Silver is an extensible attribute grammar system that supports many modern extensions to Knuth's original design. It is designed for the modular development of composable language extensions with language features and analyses to support this. So what's something they do in Silver? This is a cool example. They have this C compiler called ABLEC that's built in Silver, and it supports lots of drop-in language extensions, and you could probably write your own pretty easily. So these extensions, for example, this one to add algebraic data types to the C language, it's not even in the same repository as the compiler. It's like an external library. You can just put it in there, and now C has algebraic data types. That's amazing. And then there's another one. These are both written in Java, but this one seems to be more closely related to Java, called JastAdd. They're describing it as a meta compilation system based on reference attribute grammars, which are an evolution of attribute grammars in some form. It is designed to support extensible implementations of compilers and related tools like analyzers, transformation tools, etc. So this is a very kind of similar goal project to Silver. Not really sure what the important differences are other than the Java compiler they wrote in JastAdd versus the C compiler that was in silver. That Java compiler is called Extensible. And they did something super interesting here. They defined Java 4 through 8 without changing the old ones. They just defined the new Java version in terms of the previous one, which is not at all how compilers are built. The Java 6 compiler does not have a Java 5 compiler in it. They had to change it, right? And so this is a piece of the source code, and they're just straight up saying, okay, we're going to find a module called Java 8, import Java 7, and then we're going to, change some stuff around after that. Like, that level of modularity is not what compilers normally look like. So this stuff's pretty interesting, and it's based on attribute grammars. They've added a lot to it since then. These are some papers that kind of informed this this little slideshow here, and thank you very much. Let me know what other areas you might like to hear about, and all the stuff that you'd like to maybe add some more context to if you're more familiar with language semantics. As Lao Tzu said in the Tao Te Ching, with patience, the most tangled cord may be undone. Semantically yours,